15 billion miles. To try and comprehend that number, imagine this. If you could shrink the entire Earth down to the size of a single grain of sand, 15 billion miles would be the distance from that grain to the orbit of Mars. It is a distance so vast that it severs the normal rules of connection. It is a realm of absolute cold, utter silence, and eternal night. And there, right now, drifting through this frozen void, is a machine. It's a machine built before the first cell phone, before the internet, by engineers who are now in their twilight years, using slide rules and soldering irons. Its name is Voyager 1, and a few months ago, it started to scream. For over 46 years, Voyager 1 has been the overachiever of the space age. It gave us the first detailed portraits of Jupiter and Saturn, discovered active volcanoes on a moon called Io, and then just kept going. It became the first human-made object to enter the space between the stars, the interstellar medium. It has been a quiet, dependable pioneer, sending back a constant stream of ones and zeros that scientists translate into the secrets of the cosmos. But a few months ago, the music stopped. The stream of coherent data, the poetry of science translated into binary, suddenly turned into gibberish. A repetitive, nonsensical pattern, like a broken record skipping on the same scratched groove. For the engineers at NASA's Jet Propulsion Laboratory, the team that has been caring for this machine longer than most of them have been alive, it was the sound of a flatline. Voyager 1 was declared clinically dead. It was speaking, but it was speaking in tongues. And 15 billion miles away, with no Hubble telescope to zoom in for a look, they had to figure out why. This is the story of that diagnosis, the incredible long-distance surgery that followed, and the final, desperate stand of a dying pioneer. To understand the problem, you have to understand the isolation. A command from Earth travels at the speed of light, which sounds fast until you realize it takes 22.5 hours for that signal to reach Voyager. Then, it takes another 22.5 hours for its reply to crawl back to us. A single round-trip conversation is nearly 2 days long. You can't just reboot and see what happens. Every attempt to diagnose the problem is a 45-hour gamble. When the gibberish first started, that's what the team had to do. They'd send a command, wait a day, get a response that was still nonsense, scratch their heads, and try again. For months. The probe wasn't completely silent. It was still accepting commands. Its carrier signal was strong, but its scientific voice, the flight data system that packages all its observations for transmission, was having a stroke. The flight data system is the probe's brain. It's a computer with 69 kilobytes of memory. To put that in perspective, the average smartphone camera takes photos that are 500 times larger than Voyager's entire operating system. It's a computer from the era of Atari, running on code written in a now obsolete language called Fortran. To troubleshoot it, engineers don't Google it. They have to pull out binders of paper schematics from the 1970s, yellowed with age, and trace the circuits by hand. The repetitive, nonsensical loop was the only clue. It was like a patient in a coma, only able to twitch one finger in a steady rhythm. The team realized that the flight data system wasn't transmitting science data, and it wasn't transmitting engineering data. It was just looping. A corrupted piece of code was telling the computer to get stuck in a holding pattern, unable to do anything else. But where was the corruption? In the code itself? Or in the hardware that stores it? They devised a plan. A risky, long-shot plan. They called it a memory poke. Imagine the probe's memory as a vast city of tiny lights. Each light is a bit, a 1 or a 0. The team's goal was to find the one flickering streetlight that was causing a city-wide traffic jam. To do that, they would have to ask Voyager to send back a memory dump, a complete map of its own brain. They sent the command, "Show us what you see." 45 hours later, the data began to trickle in. It was painstaking work, comparing the received memory map against the original blueprints. They were looking for a single bit that had flipped from a 1 to a 0, or vice versa. A single, corrupted character in a library of millions. And then, they found it. A single chip, a tiny sliver of silicon that had been flawless for 46 years, had finally failed. The culprit wasn't a software bug. It was a mechanical failure. The chip had likely been degraded by decades of exposure to two silent assassins, heat and radiation. For years, the constant cycling of temperatures and the relentless bombardment of high-energy cosmic particles had been slowly damaging the physical structure of the silicon. Finally, one section of the chip just wore out. It was no longer able to store information. Any code that tried to live in that neighborhood would instantly become corrupted. They had found the ghost. They knew exactly which chip had died. But there was no replacement. No hardware patch. You can't swap out a circuit board 15 billion miles away. The chip was dead. The part of the memory where the essential flight data code resided was now a digital graveyard. The mission, it seemed, was over. Unless they could convince the computer to simply move. The solution was as audacious as it was simple. The flight data system's memory wasn't all used for code. A portion of it was reserved for storing the variable science data, the plasma wave readings, the magnetic field measurements. It was the scratch pad, not the instruction book. The team's idea was this: what if we took the code that was corrupted and moved it? What if we took the instruction book and carefully copied it, page by page, into the empty spaces of the scratch pad? It sounds simple, but it was a feat of architectural genius. They had to identify every single line of code that resided on the failed chip and rewrite the entire operating system to work around that now voided address. They had to reorganize the computer's brain, making sure the data storage didn't try to overwrite the code they'd just moved. They had to do all of this using a 46-year-old instruction set, with paper manuals and a 45-hour communication delay. Every command they sent was a roll of the dice. Move this block of code here. 45 hours of nail-biting silence. The probe would reply, command received. Then another 45 hours to see if it worked. It was a high-stakes waiting game played across the solar system. Weeks passed. One by one, the pieces of the code were carefully relocated, like moving a delicate library out of a flooding basement. Finally, on April 20th, 2024, the last command was sent. The command that would, if successful, bring the Pioneer back to life. The team at JPL waited. You could hear a pin drop in the mission control room. Then, the signal started coming in. For the first time in 5 months, the data wasn't gibberish. It was a clean, intelligible engineering report. It was the probe's vital signs. A heartbeat. The patient had opened its eyes. Voyager 1 had been resuscitated from its digital coma. A brilliant, desperate hardware hack had bridged the interstellar gap. It was proof that even a half-century-old machine, built with technology that now belongs in a museum, could defy the cold finality of the void. So, what is it like out there, 15 billion miles from home? What is Voyager 1 sensing with its newly revived mind? Its instruments are measuring the faint hum of interstellar plasma, the thin soup of material that fills the space between stars. It's detecting cosmic rays, particles accelerated to near the speed of light by distant supernovae. It's feeling the gentle push and pull of magnetic fields that don't originate from our sun. It is our first, and so far only, physical sensor in this unexplored ocean. But the revival comes with a cost. The probe is on life support, and the power is running out. Voyager is powered by plutonium-238, which naturally decays over time. Every year, the generator produces 4 fewer watts. To keep the resuscitated probe going, the mission team has entered a new, minimalist phase. They are now carefully rationing every remaining watt. Heaters have been turned off, letting the probe's instruments freeze to temperatures they were never designed to withstand. Non-essential systems have been powered down for good. Every watt saved is a watt that can be diverted to keep the transmitters warm and the scientific instruments humming, just a little while longer. It's a strange and poignant reality. The people who built Voyager 1, who held it in their hands and wished it well, are mostly retired or have passed away. The current generation of engineers caring for it are the digital natives, the grandchildren of the original team, reading their grandparents' notes to keep the family heirloom alive. But this is not a story without an end. The power is finite. The plutonium will continue to decay. By the mid-2030s, likely around 2036, the generator will no longer have enough power to run a single instrument. Voyager 1 will fall silent for the last time. It will continue its journey, of course, a silent monument. But its voice, that frantic, binary whisper we worked so hard to save, will be gone. It will become just another piece of space debris, a ghost ship. But it will not be empty. Affixed to its side is the golden record, a time capsule of Earth. It contains the sounds of wind and rain, greetings in 55 languages, and a map to our solar system, intended for any intelligent being that might find it billions of years from now. So, what does the end of a mission actually look like? It's not an explosion. It's not a crash. It's a gradual, quiet fading. It is the last watt of power being consumed, the final bit of data being sent, and then the long, eternal silence. But before that silence, there was this moment. A moment where a brilliant hack, a long-distance gamble, and the stubborn spirit of exploration reached across 15 billion miles of nothing and said, "Not yet. We're not done yet." We saved a dying pioneer, not just for the science, but for the principle, to prove that even at the edge of the universe, we refuse to let go. Voyager 1, still going, still listening, still waiting for the next command from home.